Now, here is the answer that we start with. We set this hypothesis up as a skeptical foil, the null hypothesis, which is symbolized by H sub 0. The null hypothesis always says, when we ask the inferential question about a relationship in a population, the null says this: no relationship exists in the population. Females and males give identical ratings to the Democratic Party, no gender difference. The null, the first line of attack for the null is to say, look, if you divide the entire unseen population up on the basis of gender and calculate a population mean for females in the Democratic Party rating and a population mean for males, and you subtract those two means, the true mean difference is 0. Well, our comeback would be that how did we obtain this, say, 5-degree difference we see in our sample? So here's the null's comeback. Any apparent relationship that we observe in a sample, like this 5-point difference that we found, was produced by random sampling error when the sample was drawn. So the 5-point gender difference is accounted for by random chance when the sample was drawn. You can see where we're heading with this. We're going to eventually calculate a mean difference between females and males, which we've already done, but then we're going to ask how much of that 5-point difference is random noise. Is there enough random noise in that difference to account for the whole 5-point difference? So our hypothesis, which is the alternative hypothesis, which is represented by H sub A, says that women do in fact give the Democratic Party higher ratings. This is called the alternative hypothesis and labeled H sub A. In order to have confidence that our hypothetical difference, we say we have a theory based on the gender gap, and we were expecting women to have higher ratings of the Democrats than males, and so we think the difference is produced by a systematic process. In order to have confidence in the alternative hypothesis, we must show that H0's version of events, the null hypothesis's version of events, it all happened by chance, is sufficiently implausible. That we accord the null hypothesis really an inordinate amount of territory. We have to be very sure the null hypothesis is incorrect in order to reject it. So we stack things in favor of the null hypothesis because there are two kinds of ways to get it wrong when we make an inference: type 1 and type 2 error. Type 1 error is bad error. Well, they're both bad errors, but this is worse error. Type 1 error occurs when the researcher infers that there is a relationship in the population, when in fact the null hypothesis is correct. There is no relationship. So for example, suppose based on a sample we infer that women do in fact give the Democratic Party higher ratings than men. If that is not true in the population, then we've committed type 1 error. And see, that's bad because I think that's worse because we're saying something's going on when in fact nothing's going on. Now, type 2 error is the sort of playing it safe error, the benefit of the doubt type of error. Type 2 error occurs when the researcher infers that there is no relationship in the population. Based on our sample, we say, well, we're just not sure enough that a relationship is going on in the population, when in fact there is a relationship. So we're not rejecting the null hypothesis, we're embracing the null hypothesis in type 2 error, when in fact in the population we're actually correct. This, I think, dramatizes a sort of asymmetry in inference that we have to get used to. Here's where we want to be. If HO is true, H0 is true in the population, and based on our sample, we don't reject the null hypothesis, that we've made the correct inference. That's good. If in the population H0 is false, that for example, in the population women do give Democratic Party higher ratings, and we reject the null hypothesis, then we've also made the correct inference. But the two types of error are dramatized here, or represented here. Type 1 error, HO is true, there is nothing going on in the population, but we mistakenly reject the null hypothesis. That's type 1. Type 2 is up here. H0 is in fact false, but we just don't have enough confidence to say that, so we don't reject the null hypothesis. That's type 2 error. So we bias our inferential mistakes, if you will, toward the type 2 error end of the spectrum. We always begin by assuming that the null hypothesis is true, and we set a high threshold for rejecting it because we wish to avoid type 1 error. So we're very conservative in this sense. Here is the inferential question. We ask, if in the unobserved population the null hypothesis is true, make that assumption, how often by chance will we obtain the relationship that we observe in the sample? Clearly, if the null hypothesis could explain our results, say 25% of the time by chance processes would produce our results, say 25% of the time, or 30% of the time, or even 15% of the time, we would probably say, well, that's pretty frequently, so we won't reject the null hypothesis. What creates some confusion for students is that we also extend the null hypothesis's territory, if you will, all the way down to 6 times out of 100. So if we have a set of events that could be produced by chance 6 times out of 100, we still don't reject the null hypothesis because that is too frequently given the standard that we apply. So this is the 0.05 level of significance. If the answer to the question is more than 5 times out of 100, we do not reject the null hypothesis. If the answer is 5 times out of 100 or less, we reject the null hypothesis. So in statistical significance and hypothesis testing, we have to be, our level of confidence is, our definition of a rare or improbable event is an event that occurs 5 times out of 100 or less frequently. Our definition of a plausible or even probable event is any event that occurs 6 times out of 100 or more frequently. That's the cutoff.